right, let us begin together. I feel bad moving on to announcements because there's some heated conversations going on up front here about this code. We'll come back to it. I'll give you more time, and then I'll go through it with you in a moment. Don't forget office hours, Monday, Wednesday, in the morning, 9 to 10:30. Exam scores were posted yesterday, and as a whole, class did pretty good. Happy with what I saw there. That may not be your individual feelings on the exam, and if that is the case, and you'd like to see improvement between exam 2 and the final, a few recommendations. One would be to go over the exam yourself and look at what you got right and wrong, review those problems, and once you have done that, if you want to talk further with me about your approach to the tests, come by during my office hours or talk to me after lecture to arrange another time to meet. I'm going to ask maybe not coming Monday as homework is due, and I might not have a whole lot of sit-down time with you on Monday, as I'll try to get people through that want to do homework and want to go off and see an eclipse. But that's something that I would probably put on my to-do list sooner rather than later. Now, if you need just a simple review of a few of the problems, supplemental instruction is probably going to have some element of exam review in their sessions this week. At TA office hours, you could also bring problems into there too. But if you want a more thorough review of how you did and what you did and what other else I can recommend for the future, my office hours are open for something like that. Okay, what else? Schedule. This week, if you haven't been to lab yet this week, lab 11 is in front of you. It's another array lab. And next week, lab 12, we're going to need chapters 9 and 10. So I'm hoping by the end of lecture today, I can start on that and then push farther on Tuesday to have you prepared for lab 12. Homework 6 is still pending. I've advised on Tuesday. I'll advise again here today that there's a lot of exciting things going on between now and the homework due date, and you're best off getting that done sooner rather than later. We're working to try and offer the usual office hours on Monday, but a lot of our TAs want to go south to be in totality. So watch for an update on Brightspace if we do have to offer any alternatives or cancellations of Monday office hours. So yet another good reason to make sure you're starting and finishing early. Final exam date's just out there to float, so you know what your final exam week is going to look like. We are on Monday. Somebody said we share that day with chemistry. I apologize. I have no control over that. For those of you who have to do both in one day. More on that as we get closer to the date. Scheduling questions. Then supplemental instruction should be back to normal schedule. Now that we're on the other side of the exam, check their Brightspace site for more information. I don't know if they're going to do a full exam review session or maybe just start out with any questions that those who show up might have about the exam, but I know they want to get through current content as well as we fast forward to the end of the term. All right, so here's problem 1 again. I am asking about the loop control variable J in question 1, but question 2 is going to ask about the content of the array, which I think you're probably working out anyway. So looking at this code, what draws your attention? I guess I go to the array first. It's of size 6, but 5 elements are provided, so that's 101. And then the last element not being initialized, we follow the rule and see that if the elements provided, the number of elements provided for initialization is less than the size of the array, then remaining elements here, element, singular, index 5, is assigned a value of 0. Next, I go into the for loop, and I say I traverses the array, essentially 6 iterations, 0 to 5. And then I look at J, and I notice J always starts at size minus 1. Is size minus 1 a valid index? Yes. I'm going to take a mental note that that's a good number, 5. But I notice inside the loop, there's a decrement. So in terms of the largest possible index, I don't feel like we're going to exceed that. So we're starting at 5 and counting down. But the smallest smallest possible index. Should I be worried about a negative one? I guess, yeah, in theory I should. But do I really have a negative one index problem here? Well, when you look at the condition, the loop control expression, you notice I test first to see if j is greater than or equal to 0. So what if j was negative 1? Let's say j got all the way down to negative 1. Then j greater than or equal to 0 is false. False and anything is false. So I never actually place that negative 1 as the index in x. I never reference index negative 1 because the left side would be false. And I don't have to then worry about that being replaced in the right. So I do protect myself. Short circuits more than just trick-free things. Protect you in index range. Violation. Okay, so that's the left side. The right side, what am I doing on the right side? Well, whenever the element is odd, that would be a true result on the right of the and then the odd number would postfix increment to become an even number. But when the element at index j is even, well, then that's false, and as I said, false in anything is false. Okay, so we begin at 5 for j, and then we test, is j greater than or equal to 0 when j is 5? So when j is 5, yeah, that left side is true. And on the right side, the value at index 5 is a 0. 0 mod 2 is 0, so that would be false. So we don't get any iteration the first time we encounter that nested loop. But because we evaluated both sides of the and, index 5 changes, yes, 0 to 1. And now I'm on to the next iteration of I. I is 1, j starts at 5. So when j is 5, greater than or equal to 0 is true, and now the value at index 5 is odd. And 1 mod 2 is 1. Odd numbers have a remainder of 1 when divided by 2. So I have true and true. So I do have an iteration. Before I go there, let's remember the postfix increment. So the iteration does only one thing, that decrements j. So now j is 4, and 4 greater than or equal to 0 is true. And what about the value at index 4? It's odd. So 1 mod 2 is 1, so that's true. And I shall not forget postfix increment. So j on this iteration now becomes 3. And when j is 3, greater than or equal to 0 is true. The value at index 3 is even. Even number mod 2 is 0, and that makes it because I evaluated the right side, the element at index 3 increments from 0 to 1. Next, the while loop terminates. I'm at the end of the for loop. At the end of the for loop, I goes to 2, and j starts at 5. So when j is 5, greater than or equal to 0 is true. But the element at index 5 is currently even, and that would make the right side false. So no iterations, but index 5 was evaluated, therefore incremented. Well, I think we're already on to the 4th iteration here with I. I goes to 3 every time. J starts at 5. When j is 5, that's true. It's greater than or equal to 0. How about the right side? 3 mod 2 is 1. That's the true value. So there'll be an iteration, but let's not forget our postfix increment. And the iteration takes j from 5 to 4. When j is 4, greater than or equal to 0 is true. What about that right side? Value at index 4. Even. Even numbers, mod 2, have no remainder. That's false. But we did evaluate that right side. So that element is execute, changing index 5 to 5. On to the final iteration. Start at 5. 5 greater than or equal to 0 is true. Value at index 5 is odd, so that's true. Increment, iterate. Iterate means decrement j. So now j is 4, which is greater than or equal to 0, and the element at index 4 is odd. So we'll have another iteration. Don't forget the postfix. And now j becomes 3. When j is 3, is that greater than or equal to 0? True. And the value at index 3 is odd, so that's true. So index 3 increments, and j becomes 2. Now j is 2. Is that greater than or equal to 0? Yes. Is the value at index 2 odd? Yes. Increment the value at index 2, and now go to index, or j decrements from 2 to 1. And how about 1? Greater than or equal to 0? True. And the value at index 1 is even, so that means false. So our loop with j as the control variable will stop. But because we did evaluate that right side, we have to increment that element at index 1. And now, since j is done, I will increment, and 6, we do not iterate for 6. And we stop at that point. So question 1, what do I have on the screen? Question 2. Question 1, did find j with the value of 1 as the terminal j. And then what about question 2? What were the values of the array? Up top here, 1, 1, 2, 2, 4, 6. And that makes A the correct answer for problem 2. Which 2 answers should have been eliminated most quickly? There's a pair of them. Yeah, I think C and D should have been, right? You shouldn't have ended up with odds over there on the far right. Get ready. All right. Any other questions? Complex problem. Rehearsing this organization for exam-like problems. What page are we on? I said 128. In the notes to begin today, one last example in arrays before I want to move forward into chapters 9 and 10. And here's my problem. And I'm going to sum this in a pair of methods. And I'm going to call one method the less efficient method. I'm sure it could be, it's not the least efficient. I'm sure we could do worse. Ultimately, we want to do better. And we want to discover what might be some measures of efficiency to consider as you put these final assignments together dealing with larger data sets, which mean larger arrays, which might mean larger loops. But here's my first approach. We're going to see it's logically correct. Begin to explore what makes it less efficient. The problem. Given the array, here it's an array of size 6, I want to send it to a function, and in that function, I want to reverse the elements. I want to reverse the order of the elements. Maybe there's some benefit to that later in my program. That's the task. In this less efficient approach, I'm going to send x from main. X is containing 135246. Then in the function, I'm going to create a local variable y. What happens to the local variables when functions go away? When functions return? The variables go away. Y will disappear. And I can't return y from a function. Why don't we return arrays from functions? Because they're passed by addresses. It's the changes within that will matter. And if I reverse x into y, x is not changed in any same way, and will be in the same state when the function terminates. So I got to make manipulations to x, and after I reverse x into y, I'll then copy in the same order the values of y back in. So x does end up with its elements reversed. This is my less efficient approach. I will move over to Vicarium and attempt some coding for you now. We're actually going to write a pair of functions. Let's see, I need to set up my size. I had 6, right? So in main, I'll have x of size 1, 3, 5, 2, 4, 6. Those were my numbers, I believe. And the pair of functions I'm going to create, one will be called print array. This code is going to look like the printing operation in the second quiz question, where I go through and print the contents of an array. This can be very helpful. Hopefully you've stumbled upon this without formal introduction. This can be very beneficial to problems like you're working on in homework and lab, because you have to do things like generate the data set. Okay, let's print that content, make sure it's correct. And then you might have a first manipulation. So let's print that content, make sure it's correct. And you may have a few manipulations before you get to the final results. Now, in the final program, it might be like seed and then results. How do I know what happened on the intermediate steps? I may only recognize that my final results are incorrect. Throwing these print statements, these print functions, these diagnostic print functions around within your code can be very beneficial to make sure your progress is logically sound, that you're building good logic on top of existing good logic. So I'm going to call my print array function first, and then I'll reverse array. And then I'd like to do these two things again. And then one more print on the way out. So once this is finished, original array is displayed, reverse it, show the reversed elements, and then re-reverse it, and the final print statement should show us back in the original state. Main function question. Then I need to write some function declarations. So both of these functions are void. Print array is the array passed to the print array function. Is it passed by address? Yes, whole arrays are passed by address. Is a print array function going to manipulate any contents of the array? Probably shouldn't. Like, can you stop a whole array from being passed by address? But the second function, we do benefit from that pass by address, the reverse array function, because I want the array to emerge in the reversed form. Declarations in place, main functions in place. Let's get into the definitions. Let's start with print array first. And once more, this will look like the second quiz question. I need a for loop to go through the array. And I will print on each iteration one integer followed by a single space. What this will do for me is it'll show the elements with spaces in between, but it'll show them on one line. Now for a size 6 array, if I did one element per line, that's not terrible. But as you deal with larger data sets, boom, go off the screen quickly. And printing them on maybe one row, or printing like say 5 per row, might make the whole data set easier to review. Then, let's see, I'm missing my closing curly brace. Then I might just throw an extra print statement in here. Contents of the array, something like that. Do I have a new line? I don't have a new line in here. Where do I want my new line? I think I want it to appear after the form. So I'll see the current contents of the array 3 times. Original, reversed, re-reversed, back. The original state. Can be helpful as you're working on current assignments. So let's go to reverse array next. So void reverse array, and I'll have x here. And along with x, I have a loop control variable, and I have my second array the array, element by element, and I want to copy into index I of y. So index I of y is the left side of y. I want to copy what's on the right side of x. How do I access the element on the right side of x? Well, that's at index size minus 1. Is that loop sufficient? Does this copy the last element to the first? But then what about the second element and the third? Well, it copies the last element 6 times. I have an array full of 6. That's not what I want. It works for the first iteration, but how do I revise the expression that references the index on the right of the assignment? How do I modify that expression so that as I increases 0 to 5, the expression being referenced would decrease? There's a part missing. So a subtract by the index. Let me ask this. I've taken out the constant 1 and I've replaced it with I. So size minus I is going to become smaller as I increases, right? Concerns. We never get index 0 because the range here is going to be from what? What's the smallest index referenced? The largest, smallest index. 1. What's the largest? I starts at 0. It's 6. So it goes 1 to 6, so we'll have 6 iterations. But I don't want 1 to 6, I want 0 to 5. Well, yeah, I shouldn't have pulled the constant 1 out. I should leave it in there. So size minus I minus 1. This will reverse the elements as I in y goes left to right through the array. Size minus I minus 1 will work from right to left, from higher index to lower index as I traverse through x. So now y, after this loop, y contains the reversed elements of x. But y goes away, as does I, when this function terminates. I need my changes to be to x. So I have a second loop here for I is 0. While I is less than size, I plus plus. And here, x index I needs to be established. What do I want to assign to x index I? I want to take and put what at x index 0. I want to take what's currently at y index 0 and place it at that same index of x. Remember, y contains the reverse elements of x. So copy by element from y to x. Why not just x equals y? It works in MATLAB, right? I think it works in MATLAB. Does it work in Python programmers? I'm trying to find a Python programmer who might not have. Yeah, you can copy a whole array in one statement. You can do that. It wouldn't surprise me if you could, but you can't. See? And that goes back to something I think we talked about on Tuesday. What does the name of an array represent? Memory address. I'm not interested in copying memory addresses. I'm interested in copying what's in that memory. So I need to go element by element here. I can't do a full array operation in one statement. Question? So, yeah, we're getting into the weeds here. Can I talk about that maybe on Tuesday? Yeah, so what I would have is maybe 2 variables referring to the same memory, but I wouldn't have multiple copies of that memory. That gets deep. Let's come back. We've got time next week. But here now, I think I've got this successfully working to take the elements of x, reverse them into y, and then copy them from y back into x. Okay, let's see. How'd I do? Human compilers have any opinions before GCC? Lets me know how I did. Original array, reversed. Remember, I called it again, that re-reverses it back to the original state. So it works. Why worry about matters of efficiency? Says no engineer ever. Is there a certain measure of efficiency? Is there an element of this program that leaves you a little bit uneasy this time? array, or at least without a second array. I actually need a second variable. This second variable is a single integer. What's a single integer cost in memory? Very little. In comparison with a second array. So here's the approach. My integer array has the numbers as sent by me. This new variable temp is created, and I value index 5, the last element, the right element of the array. And I move it into temp. What that permits me to do is overwrite that element, value at index 0 on the left. One copied from the index 0 to index 5. Some moment in time, I have 2 1s in the array of 5. Fear not, 6 is safe, reintroduced. It's reintroduced over the 1 at index 0. So that's what's first and last element. That's my next move. Let's go in to the second element and the second to last element and exchange those. So 4, somewhere safe. Copies of 3 in memory of this array for a moment in time. And then reintroduce the 4 over the original 3. So now first and last elements have been exchanged. There's just a pair in the middle that needs my attention. So the 2 moves next into the temporary location. Then the 5 can be copied over the 2 5s for some fraction of a second in time before the 2 can be reintroduced. And now I've reversed the array without needing a second array. Just one extra variable. Far less than a second array. Significant when the data set size is large. I'm going to put this in code form now. Going back into Vicarium. And let's reopen our reverse array program. So here is my current reverse array. And what I would like to do is make all of this previous version inactive. But I'll keep it around. Just so for a moment I can remember the errors of my previous ways. But redemption is here. I will need to create another variable. I got to create that temp variable. So let's go after my loop control variable and create temp. And then the for loop that we all use to traverse an array. And what were my steps? I took temp and I assigned it to the right side of the array. So that's at x index size minus I minus 1. And then on this right side, size minus I minus 1, I am going to copy the value at index I. What's my last move? Reintroduce at index I the value that was placed into the temp. Skeptics, great. Question everything. Let's see. I see some head shaking. There's doubts. Hang on. I want to show them the problem first, and then I'll have you guys fix it. Those of you that see the problem. Let's escape out of full screen mode, out of insert mode, recompile. Hopefully I didn't make it good. It wasn't a compiler error. It was a logical error. I think several of you were concerned about. What do we see here? We see original array, original array, original array. Did I not reverse anything ever? No, I did. But go back to the original drawing that I had here. How many times did I need to make these swaps occur? In a 6-element array, I need how many swaps? 3. I need 3. I swap the first 3 with the last 3. How many iterations do I have in the code I wrote?
We're scaring those things away.
6. So on the first 3, I swap with the last 3. But what happens on the last 3? I swap them. So in this one loop, I not only reverse, but I re-reverse. And it sends it back to the original state. So clearly we have a problem. Let's go back into the code. saying loop control expression is currently I less than size. You would like to take that and divide it in half. Size divided by 2. So how many iterations now? 3. Swap the first 3 with the last 3, and that does it. Skeptics remain. I appreciate.
This is for you.
Let's compile and run. Did it work? It worked. Where may doubt still lie? Does this problem work for general data sets? Or has this solution been just narrowly focused? What are you concerned about? If the number of elements in the array is not even, but does this still work there? Okay, so I will entertain that idea. Let's change size from 6 to 7, odd number. Let's add a 7th element to the array. How about some ones? Ones are good. Okay, so there's my new element. So size is changed to 7. A new element is added. Let's go back to the process here. Let's go back to the process. How many iterations for size being 7? 3. But there's 7 elements. There's 7 elements. There's going to be 3 iterations. You're going to swap the first 3 with the last 3. What's the 7th element? It's the middle one. Where does the middle one go? It doesn't go anywhere. You can make it iterate one more time. Swap it with itself. What does that gain? It's the waste of an iteration. Waste of an iteration. I think we're fine. I think we're fine even for an odd number of elements. Let's save, recompile. So what were the measures of efficiency? One, I think was most clear, was the second array. Problems you're currently working on, I think can be solved in one array. Or one array solutions. But what other improvements did we see here between the first version and the second? It's not only memory that I believe we benefit from, bottom of page 128, but I believe the number of iterations has been slashed. I no longer need to go through the entire data set twice to make this happen. If you're measuring purely iterations, what fraction of iterations do I have in the new versus the old? Not half. I went through the entire array twice in the original. How far do I go in the new? Halfway. So you'd be like, it's a quarter. But you can't really say every iteration is equal. The previous versions had 1 statement per iteration. This one now has 3. But there is a savings there nonetheless. You do not have to traverse the entire data set twice. And that's a savings in time. When we save instructions, we're asking less of the processor. That's a reduction in time. And the wastefulness, the efficiency, really becomes apparent when the data sets are lower. Size 6, you're probably not noticing any difference. If you ever submit through Vicarium and you get an output says what, timed out error, that could be an infinite loop. That could also be an indicator that rhythm needs to be a little more efficient. And you could say, when I type a.out, it works fine. Well, when you run a.out, I don't think we have a firm limit on how long it takes, but when on submission, it does. It does have a limit. So you may have to take a step back and go, where can I save on efficiency so I don't time out at submission time through Vicarium? So keep an eye out for that error, that timed out as your output when you submit. Questions? Let's break away from chapter 8 for a moment because I do need my 7 minutes that remain to begin our conversation into what will be necessary in our lab next week, and that's on page 147 of your notes. pointers, pointer variables, addresses. How have we made it this far in the class with addresses? Where did we see addresses first? Actually, scanf was our first address operator usage, and then that was our only address operator usage until we reached the latter half of function, where I said, hey, pass by value, and this alternative pass by address. So we saw a little bit of pointer and pointer operations at that time, and then things were kind of quiet when it came to memory until we got now here to chapter 8. Because I said when you pass a whole array to a function, it's a pass by address, but when you call a function and pass a whole array, the only parameter is the name of the array. Therefore, the name of an array is a memory address. So that comes back again. We have addresses, we have arrays that store addresses, we have pointer variables that store addresses. Is there a connection there? Yes, we begin to bring that together here in chapters 9 and 10. And what we ultimately want to do is we want to get over one of our current limitations with arrays. And it's not a limitation that you have in Python or MATLAB. In those languages, if your array needs to grow during the program, you just make it grow as the programmer. And the computer handles how it grows inside the memory behind the scenes. In C, we've been setting up these arrays of a fixed size. What's the concern with fixed size arrays? They can't grow nor shrink during the execution of the program. The problem is, what if you need more memory? It's not there. I guess you could say, open up the source code, change the size constant, save, recompile. Do you do that in Excel whenever you need more cells? Open up the source, save, right? It kind of grows dynamic. So that's where we want to be able to go to request the exact amount of memory we need, because requesting an insufficient amount is a concern. But what about just, why not make every array size 1 million? Well, first of all, that could be insufficient. Second of all, it could also be way too much. So we're looking to go more for an exact amount that we need. And to do that in C, we need to have a little more control of what's going on in memory. Because we don't know the size of our data set until the program is running, then I have to request the memory at that time, and I need some way to keep track of where that memory is. And that's what a pointer does. It points to different locations in memory. Hey, computer, I need enough memory for 50 integers. Okay, here it is. And it lets you know the address, and then the pointer takes it from there. That's where we're going to work our way towards. Starting today, but mostly on Tuesday next week. So in this example, you have on page 147, there's two character variables, A and B. And they can store enough, they have enough memory to store a character. A is storing uppercase X, B, Y, lowercase y. But in my little code segment there, I'm printing not the contents of A and B, but where they're located in memory. And it's that long hexadecimal value on the right. I think I did this in lecture on Tuesday with arrays to show you that when you send a whole array to a function, it isn't passed by address. So here you can see these two arrays have been given memory at those unique locations. You have no control over that, but you may rightfully observe what? How are they? Where are they with respect to each other in memory? Where did the computer put A and B? Can you decipher that from these? You know a little bit. They've been put where? Side by side. I think you can tell enough that F and E are off by 170 F and 170 E are just next to each other. Because remember, characters require a small amount of memory. So the address operator will return the address. Without the address operator, I'd have to change from %P to like %C, and then I would see the uppercase X and the lowercase y. So every variable has an address. We can get that. Data variables. We can retrieve the data variable address by using the address operator. Pointers are variables, but what they store is not like integer data, floating point data, character data, but rather what they store is the location of that data somewhere else in the computer's memory. And so how we've used pointers up to this time in the class is with passing by address to functions. You pass the address of X and the address of Y. That's the call. But in the function definition, you needed a pair of pointers to receive those addresses. And it was actually in the first line of the function definition where those variables were declared and initialized. But what we need to do now is actually declare our pointers within the local declaration section of the function. We haven't done that yet. And here you're seeing examples of how that's done on the left. First of all, notice the asterisks. The asterisks indicate that these are not data variables, but pointer variables, or the book might say address variables. And what I've done on the left is I've shown you a sample and an alternative. They're both interchangeable. Do you view the asterisk as being part of the data type? Then maybe you favor the bottom. If you think it's more of associated with the name, then you kind of do what you did at the top. I choose the top more than the bottom. I'm sure there's threads on the internet where people obsessively argue about this, do better things with your time. But the bigger point is on the right. You're going to need an asterisk to declare the variable as a pointer variable, whereas if it's not there, then it's your standard data variable. Our time has expired. I hope this weekend brings a lot of excitement to you before I see you next on Tuesday, and one of those exciting things is wrapping up homework number 6.